Statistical models and interpretation. Choosing the right statistical model. Today, we're going to discuss how to choose the right statistical model and how to interpret results responsibly. Statistics is not about memorizing formulas, it's about selecting the right tool for the right question. Across disciplines, whether you're analyzing gene expression, educational outcomes, public health trends, engineering data, or AI model performance, the underlying logic remains the same. Your choice of model directly affects how your results are understood. A poorly chosen model can distort your conclusions, while the right model strengthens the credibility of your research. Why statistics matter. Statistics is what transforms raw data into meaningful evidence. Raw numbers alone do not provide answers, they need interpretation. Statistics helps quantify uncertainty and protects us from drawing conclusions based on chance or bias. It also ensures that findings are reproducible and reliable. Across fields, statistics supports critical decisions, from public health policies and medical treatments to engineering safety and AI model evaluation. At its core, statistics is about making structured, informed decisions under uncertainty. Types of variables. Before choosing any statistical model, you must first identify your variable types. Continuous variables, like height or blood pressure, behave very differently from categorical or binary outcomes. Misclassifying your variables can lead to inappropriate tests and invalid conclusions. For example, treating ordinal data, like survey ratings, as continuous without proper justification can distort your results. The accuracy of your analysis begins with correctly understanding your data. T-test. Use a t-test when you are comparing the means of two groups. This could be an independent comparison, like treatment versus control, or a paired comparison, such as before and after measurements in the same subjects. T-tests assume that the data is approximately normally distributed and that the variance between groups is similar. They are widely used across fields, from comparing blood pressure in biomedical studies, to testing material strength in engineering, to evaluating teaching methods in social sciences. The key is simple. Use a t-test only when your question involves two groups. ANOVA. When comparing 3 or more groups, ANOVA is the appropriate choice. Using multiple t-tests in this situation increases the risk of false positives, also known as type 1 error. ANOVA allows you to compare all groups simultaneously while controlling this risk. However, the analysis doesn't end there. You must perform post-hoc tests to identify which groups differ. ANOVA also assumes normal distribution and similar variance across groups. It is widely used in settings like multi-arm clinical trials, public health interventions, and dose-response studies in biology. ANCOVA. ANCOVA is used when you need to adjust for covariates that may influence your outcome. It helps control for baseline differences between groups, improving the accuracy and statistical power of your analysis. By combining elements of regression and ANOVA, it allows you to compare group means while accounting for additional variables. This is especially useful in fields like clinical research and education. For example, adjusting for age in clinical trials or socioeconomic status in educational studies. Regression. Regression is used to model relationships between variables. Linear regression is applied when the outcome is continuous, while logistic regression is used for binary outcomes. It also allows for multivariate modeling, where multiple factors are analyzed together. Regression can be used for prediction or for explaining relationships within data. It is widely applied across fields like economics, public health, and AI. For example, predicting income based on education level, or estimating disease risk based on biomarkers. Correlation. Correlation measures the strength and direction of association between variables. Pearson correlation is used for linear relationships, while Spearman correlation is rank-based and useful for nonparametric data. It is commonly used in exploratory analysis to identify patterns. However, a key principle to remember is that correlation does not imply causation. Just because two variables move together does not mean one causes the other. Nonparametric tests. When the assumptions of parametric tests are not met, nonparametric tests provide a safer alternative. They are especially useful for non-normal data, small sample sizes, or ordinal variables. Tests like Mann-Whitney and Kruskal-Wallis are commonly used in these situations. In fields like social sciences, where survey data and smaller samples are common, these methods are widely applied. Choosing the right test depends on your data, not just your preference. Chi-square. Chi-square is used to compare categorical variables and test whether they are independent. It helps determine if there is a significant association between groups. This test is widely used in fields like epidemiology and public health. However, it requires sufficient expected counts in each category to be valid. For example, it can be used to examine the relationship between vaccination status and infection rates. In simple terms, chi-square tests whether observed differences across categories are meaningful or due to chance. Survival analysis. Survival analysis is used to model time to event data. It focuses not just on whether an event occurs, but when it occurs. Methods like Kaplan-Meier curves and the Cox proportional hazards model help analyze these timelines. A key advantage is that it can handle censored data, where the event has not occurred for all subjects during the study period. While widely used in fields like oncology, it also applies beyond medicine, for example, in engineering to study system failure over time. Power analysis. Power analysis is used to determine the appropriate sample size for your study. It requires an estimate of effect size, along with your chosen significance level and desired statistical power. Conducting this analysis helps prevent underpowered studies that may fail to detect meaningful effects. It is a critical step in study design, especially for grant proposals and experimental planning. Most importantly, power analysis should always be performed before data collection begins. Effect size. Effect size measures the magnitude of an effect, not just whether it is statistically significant. Metrics like Cohen's d, odds ratios, and hazard ratios help quantify how meaningful a result is in real terms. This is especially important for decision-making in policy, medicine, and engineering. Because statistical significance alone does not tell you how large or impactful the effect truly is. P-values. P-values represent the probability of observing your data under the assumption that the null hypothesis is true. They are not proof that your hypothesis is correct. P-values are also sensitive to sample size. Large samples can produce small p-values even for trivial effects. This is why they must be interpreted with caution and always alongside effect size and study design. A small p-value does not necessarily indicate a strong or meaningful effect. Confidence intervals. Confidence intervals provide a range of plausible values for your estimate. They reflect the precision of your results. Wide intervals indicate greater uncertainty, while narrow intervals suggest more precise estimates. They also complement p-values by adding context to statistical significance. Together, they help you interpret your findings more meaningfully. Meta-analysis example. Meta-analysis combines results from multiple studies to generate stronger, more reliable evidence. It uses tools like forest plots to visualize effect sizes across studies. Depending on study variation, fixed or random effects models are applied. Heterogeneity, often measured using the I-squared statistic, helps assess how consistent the results are across studies. By pooling data, meta-analysis increases statistical power and strengthens overall conclusio. Preclinical example. In a preclinical study like this, your statistical approach should match both the design and the data structure. With multiple dose groups and a control, ANOVA is appropriate for comparing group means, followed by post-hoc tests to identify specific differences. Since measurements are taken weekly, you should also consider the time component in your analysis. And importantly, always check assumptions like normality before applying the test. The key principle is simple: match your statistical method to your study design and time points. Clinical example. In clinical studies where measurements are taken at baseline and follow-up, the data are paired. This means the same subjects are measured more than once, so a paired analysis, such as a paired t-test, is required. It's also important to adjust for potential confounders that may influence the outcome. Along with statistical significance, you should report effect size and confidence intervals to provide a complete picture of the results. The key point is, repeated measures require paired analysis for accurate interpretation. Multivariable model. Multivariable models allow you to adjust for factors like age, sex, and baseline characteristics. By accounting for these variables, they help reduce confounding and improve the precision of your results. They are widely used in fields like epidemiology and are increasingly important in ensuring fairness in AI models. Overall, multivariable modeling strengthens the validity and reliability of your conclusions. Overfitting. Overfitting occurs when a model learns the noise in the data instead of the true underlying pattern. This often results in high accuracy on training data but poor performance on validation or new data. It is especially common in AI and machine learning models. Techniques like cross-validation help prevent overfitting. Ultimately, overfitting reduces the model's ability to generalize to real-world data. Model assumptions. Every statistical model is built on a set of assumptions. These may include normality, independence of observations, equal variance, linearity, or proportional hazards depending on the model. If these assumptions are violated, your results may not be reliable. That's why it is essential to test assumptions before interpreting or trusting your findings. Strong analysis begins with valid assumptions. Statistical pitfalls. Statistical pitfalls can undermine even strong data. Issues like multiple comparisons, p-hacking, selective reporting, and ignoring null results can all distort findings. Misinterpreting trends is another common mistake. Maintaining transparency in your methods and reporting helps reduce these risks and strengthens the credibility of your work. Interpreting results. Interpreting results goes beyond simply labeling them as significant or not. You should consider whether the findings show a clear effect, a trend, or a null result. Importantly, null results are valuable and contribute to scientific knowledge. Always evaluate the clinical relevance and potential policy impact of your findings. A result is meaningful not just because it is significant, but because of what it implies in the real world. Statistical reporting. Statistical reporting should be clear, complete, and transparent. Always include key details such as mean plus or minus standard deviation, sample size, exact p-values, effect size, and confidence intervals. These elements allow others to fully understand and evaluate your findings. Clear reporting not only improves interpretation but also builds credibility and trust in your work. If you'd like deeper, more focused episodes on topics like biostatistics, survival models, AI predictive modeling, econometrics, or public health statistics, let us know. Tell us your area of interest in the comments, and we'll create detailed content tailored to your discipline. If you enjoyed this video, found the topic helpful, or believe this content could be useful to others, please take a moment to like, share, and leave a comment below. And don't forget to subscribe to the channel for more videos like this. Thank you for watching.